In this video, we'll explain how to create a magic square. We'll explain dimension and order. We'll explain cell components and how they can be expressed in an appropriate base. We'll illustrate symmetry within a magic square, and we'll explain the magic sum for each row, column, and diagonal within a magic square. In this chapter, we'll explain how to create a 5x5 magic square. Since each row and each column contains 5 numbers, we say that the order of the magic square is 5. This magic square has 2 dimensions. Later we'll explain how to create a magic square in 3 or more dimensions. Since the order is 5, we'll be working with numbers expressed in base 5. That is, we'll restrict ourselves to the numerals between 0 and 4. Since this magic square has 2 dimensions, each cell in the magic square will have 2 components, each expressed in base 5. So let's start exploring how to create a magic square. The first thing that we'll do is we'll create 2 components in each cell. And I'm going to start and I'll fill this column. I'll explain what we're doing in just a minute. As you'll see, each cell contains 2 components for 2 dimensions, limited to the numbers between 0 and 4. As we explained in the previous chapter, when we express a number in base 5, essentially what we're doing is we're exponentiating each of the components. If you don't understand what that means, please look back to the previous video. What we can do, though, is say that these numbers in base 5 represent these numbers expressed in base 10. Now what we'd like to do is fill the rest of the cells in both of these magic squares with an appropriate set of numbers. But how do we decide what an appropriate set of numbers are? Well, what we do is we work with each component in each cell separately. Let's adopt a convention that says for the first component in each cell, as we go to the right, that component will increase. So we'll have 3, 4. Since we're working in base 5, the highest numeral is 4, so the next numeral will be 0. So as we cycle around, it becomes 0 and 1. Similarly, let's adopt a convention that says as we move to the left, the second component increases. So we'll have 3, 4, 0, 1. And as we complete the grid, you'll see that each cell continues to contain 2 components. And even though I didn't write a comma in each cell, we should always remember it's there. The next thing to notice is that if we look at any particular component in any particular column, there is exactly 1 instance of each numeral from base 4, 0, 1, 2, 3, 4. If we look at the first component here, it's 0, 1, 2, 3, 4. If we look here, the second component is 2, 1, 0, 4, 3, because it's descending, or 3, 4, 0, 1, 2, ascending. The next thing to notice is the symmetry within the grid. If we look at the first component on the principal diagonal, you'll see it's 2, 2, 2, 2, 2. Again, here, if we look at the second component, it's 2, 2, 2, 2, 2. The numbers here, if we look and we express them in base 10, we'll see that's 0, 6, 12, 18, 24. Another nice thing is if we look at the components in this direction, they're going to be 4, 8, 12, 16, and 20. The symmetry that we saw when we express the magic square in base 5 disappears when we express it in base 10. The same thing will happen when we build Sudoku puzzles. There'll be a very beautiful symmetry when we use an appropriate base. It will disappear when we express it in base 10. Another thing that we'll see when we work with Sudoku puzzles is represented here. We can take a magic square and we can represent it with the numbers decimal from 0 to 24, or we could add 1 to each column and have the numbers 1 to 25. We could also add an arbitrary constant to each cell and we'd still have a magic square. More interestingly, we could multiply each cell by a number and then add a constant to that and we would still have a magic square. Here we see we have a magic square because the sum of each row and each column is equal to 60. Also, if we add all of the numbers along a diagonal, it's also 60. Same thing happens in this direction. We have 60. I hope this will have whet your interest for magic squares. If we decide that we want to build three-dimensional or four-dimensional magic squares, it's possible to build them by hand, but you'll probably find it tedious. For those cases, we'll provide some tools that will help you to both build magic squares and build Sudoku puzzles, and if you choose, to also play Sudoku puzzles. Giant Sudoku Puzzle Maker is a digital tool built upon Eclipse. The mathematical code that supports magic squares in Sudoku is written in Java. Please see the notes that accompany this video series and the last video in the series to learn how you can obtain Giant Sudoku Puzzle Maker and its source code. The word giant in Giant Sudoku Puzzle Maker means that you can create Sudoku puzzles that are larger than newspaper-style 9x9 Sudoku puzzles. You can also create magic squares whose order is an odd number and whose dimensions are only limited by the capacity of your computer. This video demonstrates how to present magic squares in numeric or tuple format. It also demonstrates how to add a constant to each cell to present zero-based, one-based, or center cell zero-based magic squares. To create a magic square, we start with the dialog and enter the number of dimensions and the order for the magic square. This presents the magic square in base 10, but let's start with the tuple representation of the same magic square. This uses the same techniques that we illustrated in the basic mathematics video. Let's start with the center column and notice that 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4 are represented along the center column of the magic square. Also note that we can trace the progression of the components within each tuple. For example, we have 0, 1, 2, 3, 4. For the first and second components, it's 0, 1, 2, 3, 4. Returning to the numeric representation, we see here that this is one-based. This means that the numbers range from 1 through 125. We can represent this as zero-based, and now the numbers range between 0 and 124. If we switch to center cell zero-based, now the center cell is 0, and we can see the symmetry within the base 10 representation of this magic square. For example, we have minus 33 and plus 33 at the ends of the diagonal, minus 57 and plus 57. We can look and we have minus 4 plus 4. If you continue to examine this, you'll see much more symmetry within this base 10 representation of a magic square.